All right, so we're going to go ahead and get started. I will introduce you, our speaker for today. And let me see. So we want to welcome everyone to the third installment, the third CHEMSEM guest lecture today. Very interesting topic, turning nuclear waste to glass. And our speaker for today comes from Rutgers University, which is a well-known, famous university. Ashutosh Goel. I'm just going to say Professor Goel. Is that okay with you, sir?
Yeah, thank you. Yeah, that's fine.
Okay.
That's fine. Thank you.
Okay, because I might stumble over your first name. So,
No,
Professor.
that's perfectly fine. It's Ashutosh, so it's all good.
Ashutosh, okay.
Right.
Professor Goel received his bachelor's in physics, his master's in physics from the Guru Nanak Dev University in India. He then went on to obtain his PhD in materials science and engineering from the University of Aveiro in Portugal. And then he, in 2014, joined the faculty at Rutgers University in the Department of Material Science and Engineering. So he's our speaker for today. His area of research is in understanding composition, structure, property relationships in oxide glasses. And today he will talk to us about, I guess, using those glasses as a way to store nuclear waste. Thank you for accepting our invitation.
Yes, thank you.
Oh no, it's my pleasure. Thank you, Dr. Desmond Murray, for inviting me over. It was actually a pleasant surprise when I received your invitation. It would have been even better. I would have loved to if I would have been given an opportunity to actually visit your university, your campus, and deliver a lecture there. But maybe next time.
Yes, maybe that could be in the future.
Yeah. All right. Hey, students. So I'm here to interact with you guys and tell you a bit about, turning nuclear waste to glass, and what is nuclear waste or why glass and everything. So what I will do over here is primarily I won't show you any graphs or any data or anything. I'll just tell you a story and some problems, a few problems what we deal with as scientists when we think about nuclear waste and turning it into glass. So I hope you will enjoy it, and feel free to ask me questions later, as many as you can. All right, because that's what I'm here for. So let's get going with it. So, so whatever research we do in my group over here, it has been funded by US Department of Energy, as you can rightfully think so, because it's the US Department of Energy that deals with all the nuclear waste management in the United States. So they fund a lot of our research at Rutgers in my group, and that's why we work on this. So having said that, story of the first nuclear weapon. I don't know what you know about, how we came across with this. How did we develop our first nuclear weapon? You must have heard about Hiroshima-Nagasaki incident, where the United States dropped 2 atomic bombs or nuclear bombs on the, Hiroshima and Nagasaki cities in Japan to end the World War II. That led to the culmination of World War II. But how did those nuclear weapons actually come into picture? How were they developed? What's the story behind them? Let's go with that. So, in 1933, 1934 time, 2 scientists, Leo Szilard and Enrico Fermi, they came up with the idea of nuclear chain reaction, what we know as nuclear fission, right? Nuclear chain reaction, controlled nuclear chain reaction. And around that, in 1934, they filed a patent, they submitted a patent to develop the first nuclear reactor. So the picture over here that you see is actually the picture of the world's first nuclear reactor that was built in 1942 at University of Chicago. And this nuclear reactor was built actually under the football stadium of the University of Chicago. So it's a historical picture, and the lady in the picture, Dr. Leona Woods, she was the pioneer who actually worked on building this nuclear reactor with these two gentlemen here. And from here, the whole journey starts. So in 1934, they filed a patent, right? And they were working on this concept of developing the first nuclear reactor and how will it be and all that. And in the meantime, they get some sort of, and this was a time when when World War II was starting, or was, it was going around, and they got some news that somehow Germans are trying to copy the research that's going on at the University of Chicago and trying to replicate it and make a bomb in Germany. And that's where it all started, where these two scientists, they went to Albert Einstein in New Jersey at Princeton University. They came to Albert Einstein and they convinced Einstein, they told him that, hey, look, we are working on this idea and we have got a fair reason, a strong, valid reason to think that Germans have got a whiff of it and they're trying to copy our research. And if they succeed in making this nuclear bomb before us, or if they succeed in building this nuclear reactor before us, they can actually make a nuclear bomb and can change the course of the history. So why don't you write a letter, because you are the Albert Einstein, why don't you write a letter to the president of the US and convince the president to give us some funding or to sponsor this program and start the nuclear weapon proliferation program. And Albert Einstein got convinced by these two gentlemen and signed on this letter. Why I'm saying signed on this letter? Because this letter was actually, the letter in the background over here, this letter was actually written by these two gentlemen here. Albert Einstein signed on it. And it was sent to President Roosevelt at that time. And President Roosevelt, after reading this letter, sanctioned the Manhattan Project, which led to the development of these bombs, Little Boy and Fat Man, bombs that were dropped on Hiroshima and Nagasaki in 1945. So in the United States, as of 2020, now we are a nuclear power, and as of 2020, we had 3,750 active nuclear weapons. We had a lot more. We dismantled them. And so I'm just going to talk about one particular site of nuclear waste in the United States, and that is called Hanford site. I don't know if how many of you have ever heard of Hanford site. Hanford is actually a desert area in Washington State, near to Columbia River in Washington State. As you can see in this map over here, it's just next to Oregon. And it's a desert town over there. The reason and this is the place where the reactors were built for the Manhattan Project. And the reactors were built over there because for the reactor to run, they needed a constant supply of fresh water, cold water, to keep the reactors cool, right? So they were looking for a river where they could build these reactors, but then they also wanted a place where nobody lives, because they cannot put a nuclear reactor in the middle of a city, right? Populated town. So that's where they found this site of Hanford site. They had Columbia River flowing next to it, and it was a deserted site. It was actually a desert. It is still a desert, and that's where they built the reactors over there. The reactor in this picture over here, called B reactor, this is actually the reactor where plutonium was produced in 1943. That was used to develop the plutonium bomb, Fat Man bomb, that was detonated over Nagasaki in 1943. Now it is kind of a historical thing. You can, get permissions and you can go in there. But once upon a time, it was actually a churning out nuclear reactor, working nuclear reactor. So eventually, after World War II ended, then we went into Cold War era. And from Cold War era, then during that era, we were producing a lot of nuclear weapons. So everyone was looking at the nuclear weapons being produced, but there, along with nuclear weapons, there was a lot of nuclear waste also being produced, right? So we extracted plutonium, we extracted uranium, or whatever we wanted to, but whatever was left over, the spent nuclear fuel and all the other materials along with it, it all became the now radioactive waste. So by the time we ended up the nuclear weapon proliferation, we stopped nuclear weapon proliferation, that was in 1988, production of plutonium ceased in 1988. We actually had more than 55 million gallons of radioactive waste already produced, which was stored in 177 tanks, steel tanks. So there are 177 underground steel tanks, right? Huge. And 56 million gallons or more than 55 million gallons of radioactive waste has been produced or was produced. So the cleanup mission began in May 1989, and it was decided that we are going to turn this waste into glass. So when I say turn this waste into glass, means we are going to make glass out of this waste. It's not that, we'll seal the waste into a bottle and, we'll cap it up and then we forgot it. No, we will make glass out of it. Right? So, just a bit of a background coming from since you all are students over here, is nuclear waste dangerous? Let's think about it. When you throw a piece of paper into a, trash bin, right? It decomposes or breaks down within a month's time. If you throw apples core, it takes around 6 months for the apple cores to decay. When you throw a plastic cup, a red Solo cup, that takes around 500 years to decay. And when you talk about nuclear waste, we are talking about thousands to millions of years for the radioactive waste to decay to its half-life. You all are chemistry students, biochemistry students, you all know half-life. I don't have to tell you about that. So that's how, slow the decay in the radioactive chemicals is, or radioactive waste is. And above that, the radioactive waste emits high energy radiation. That's the worst part of it. It emits high energy radiations. And this radiations or this energy can actually kill cells, can lead to cancer or damage other living beings. Like, for example, what happened in Fukushima disaster, right? In Japan, when tsunami came several years back, and a lot of radioactive waste got released into Pacific Ocean. It was a disaster. So can we leave this nuclear waste in the tanks forever? We have nuclear waste sitting in 177 steel tanks underground. Can't we leave it just over there? We can, but we do not want to leave the waste for our next generations, right? It is dangerous. It is highly toxic and hazardous. It is already seeping into, or it has in the past seeped into the ground. What happens if it enters the Columbia River? It enters into the food chain. You don't want that, right? So somebody has to take care of this. So what do we do now? Right? So a lot of times students ask me this: can we shoot this nuclear waste into sun or space? Like pile up everything, all this nuclear waste into a rocket and just send it over to sun. Well, it's a great idea, but think about it. Even a 0.1% failure in the rocket launch, you have got 56 million gallons of radioactive waste, 0.1% failure, and now you have got 56,000 gallons of waste spilled all over the earth, right? And even if it reaches space, who's gonna take care of that waste in the space? Someday the rocket is going to go out of life. What do you do after that? So again, back to the drawing board, we need to do something. What do we do? Let's turn this waste into glass. Now, a logical question to that is, why glass? Well, glass has flexible structure. So you must, again, coming from your chemistry or biochemistry background, I'm sure you know that glass is amorphous in nature, right? So since it is amorphous in nature, it can accommodate a lot of different elements and ions in its structure. Whereas for the crystalline materials, crystals have crystal structures like FCC, BCC, HCP. And then if you want to substitute something in the crystal structure, you will have to substitute it at one of the particular lattice points or atomic sites over there, right? So that's not the case with glass. In glass, it can accommodate a lot of ions and elements in its structure. And that's why glass becomes an ideal material in this case. And then glass is durable. For example, just look at the windows around you. You're telling me it's snowy outside, it rains. Do you see your glass window disappearing, corroding away? The glass window stays there for years and years and years, right? If glass window is that durable, think about the nuclear waste glass which we will be creating. How durable will that be? We are expecting the nuclear waste glass to stay there for at least 10,000 years. right? And then the waste produced from the production of the nuclear energy or of one person's entire life, it can be all the waste that will be produced for one person's electricity from nuclear energy can be converted to glass and be contained in a glass in this size, like in one hand. Basically, it can be contained in one hand. So basically, you can shrink all the waste into glass and make a solid body out of it, which can be easily contained. Now your waste is not liquid, it's not corrosive, it's not flowing around anywhere. You have contained it, and it's in a durable matrix. So the current strategy that United States government is following is to convert this waste into glass in a step-by-step process, and it's into a borosilicate glass. Borosilicate means a glass that contains boron and silica, SiO2, as the main formers, main components, and the rest of the components come from the waste, right? So the first step in that case is that the tanks that contain this waste, 56 million gallons of waste, right? We'll separate this waste into two parts. One will be called the low activity waste, LAW, and the second part will be called the high level waste, HLW. So 90% of this waste in the tanks is categorized as LAW, low activity waste, and the remaining 10% is known as high level waste. And you can judge, basically, when I say high level waste, it contains species that have high radioactivity. Low activity waste, it contains species that have low activity, right? So we'll divide this waste into two. Step one, separate the waste into low activity waste and high level waste. Step two, pump this waste through a processing facility, pump this waste into the melters and mix silica and boron oxide, H3, boric acid, basically H3BO3, boric acid into it, and then heat this waste to temperatures as high as 1150 degrees C to 1200 degrees C, 1200 degrees C, 1150 degrees C. And then once you have melted them, you have heated them, you have homogenized the melt, and everything is converted into glassy melt. You pour it into steel canisters, right? You can see, and the high level waste canister will be slim and tall, whereas low activity waste canister will be a bit fat and short, right? And then the high level waste canisters, they go to a geological repository, which is yet to be decided where it will be. Earlier it was Yucca Mountains, but then President Trump came, he said no, Yucca Mountain is not good. In Nevada, we are not sending it there. So it's yet to be decided. For the low activity waste glass, it will be stabilized, or it will be stored for the time being in a federal repository in an engineered building, let's say, like next to the site, wherever it will be created, wherever it will be produced, this glass, they have created a building over there, and they'll store this low activity waste glass over there for a few hundred years before it is shipped somewhere else. All right. So US Department of Energy has built this huge waste treatment plant and immobilization plant at 67 acres of area at Hanford site in Washington state. So when I say 67 acres of area, you can imagine something around approximately 50 soccer fields we are talking about. It's that big, 50 soccer fields, all right? So that big of an area has been covered to make all of this vitrification plant or the waste treatment and immobilization plant. So now to summarize so far, whatever we have discussed. So plutonium production ceased in 1988. Cleanup began in 1989. US Department of Energy is building a waste treatment plant to vitrify this high level waste and low activity waste separately. And the vitrification of low activity waste has already started in December 2023 or December 2023. They have already started making the test runs, pouring out the test melts. And hopefully in 2024, they'll ramp up the production, right? So what's the problem now? Like, why are we still working on this topic when everything is sorted out? Correct? Let's take a look. And Desmond, please, let me know whenever I am running out of time or something, so that, we can stop there and start taking questions. All right?
All right.
No problem.
We're good still.
So the $1 million question over here is that, okay, we are at a point where we can start melting the glass, where we can start converting the waste to glass. We can do that. But all of this waste to glass conversion process, all this Hanford site vitrification plant is being run on taxpayers' money. It's being run on your money and our money, right? On taxpayers' money, whatever taxes we pay. So we need to be efficient about it. We need to be, more productive about it. Can we somehow shrink the 30 years or 40 years of this operation? Can we reduce it to 20 years? Can we reduce this operation in 20 years? Because even if we can reduce 5 or 6 years or 10 years out of this whole operation, we'll save billions of dollars of taxpayers' money, right? So the logical question in this effort is, can we increase the amount of waste that we'll put into the glass? Let's say if the 100 grams of glass contains, in today's date, contains 40 grams of waste, right? And there's 60 grams of other components that we add from our side. Can we somehow increase the waste loading? Can we increase that 40 grams to 60 grams and still make a glass out of it, which is chemically durable, which will not dissolve easily? If we can do that, that will be a huge thing, right? So we need to strike the right balance. But then the challenge over here is that the nuclear waste glass is actually highly, highly complex. And over here, I'm just giving you a snapshot of what a high level waste glass looks like. So I usually joke with my students, my PhD students, that, yeah, hey, like put a periodic table and take a dart and throw it on the periodic table, whichever element it hits on, most likely that element is present in the radioactive waste. Basically, the radioactive waste or the nuclear waste tanks, radioactive waste tanks at Hanford site, they're like kitchen sink. They have got almost everything from the periodic table. This is, again, on the screen, what you see is only the high level waste glass composition or high level waste elements present in the high level waste glass. Low activity waste glass is completely different. It has even, like different set of elements in it. Some overlapping, some different. But that, what I'm trying to say is that will add more from this periodic table, more elements from this periodic table, right? So having said that, to make glass out of something so complex is challenging. It's an arduous task. So what I'm going to discuss and what I'll touch upon is 3 problems. If we have time, otherwise, I'll stop on problem 1, 2, wherever we can, up to whatever point we reach here. So now think about it. So the waste is in the melter, right? And we are melting the waste. We are converting it into glass. We have added sand. We have added boric acid. And we are now heating it to 1100, 1200 degrees C. And all of a sudden, there's a power failure, right? Or something went wrong with the melter. And now the melter has to be brought down, or the temperature has to be lowered down, right? And you may say that, oh, how come there's a power failure? It happens. It happens. Or imagine, if nothing else, Congress did not come to an agreement in the Washington, D.C., and they did not pass a budget for the next year, right? And now everything is on standstill. There is no money to run the vitrification plant. So the plant has to be stopped. In that case, what happens is the temperature of the melter starts to come down from 1150 or 1200 degrees C. It starts to come down, and we expect that at the lowest where we'll bring that melter will be something around 850 degrees C and keep it on standby over there, or 900 degrees C and keep it on standby over there until it goes up again. So now this process of lowering the temperature and making it into standby is called melter idling, right? So what happens in this case is, when melter idling is taking place, there is a term called liquidus temperature, which I hope you guys know. At least the senior year students should know what is liquidus temperature. You must have studied phase diagrams in chemistry. So when the melt comes below liquidus temperature, right, crystals start to form in the melt. Now, in this case, what happens is those crystals that are formed in the melt are spinel crystals, which are rich in iron, nickel, manganese, like all transition metal cations. And these spinel crystals, they have a lot high density. We are now talking about a density of 5 grams per centimeter cube or more than that, whereas the melt has a density of around 2.5, 2.6 grams per centimeter cube. So what happens when you have got melt of density of 2.5 grams per cc and the crystals have density of more than 5 grams per cc, the crystals settle down in the melter. And they not only settle down in the melter, over here, but they also settle down in the spout of the melter, right? And then another thing that happens is at the spout, at the mouth of the melter, at the spout of the melter, since this spout of the melter is in contact with the air, right? So it cools down really fast, really quick. So over here, the crystals also start to form. The spinel crystals also start to form here. Now, what happens? When these crystals start to form, now they start to obstruct the flow. They start to restrict the flow of the melt, and eventually they choke the melter. So now the melter cannot perform. The flow, the melt cannot, come out of the melter in a proper way as expected. So what, now now the melter goes out of, it's out of commission. We cannot use this melter. So the aim is not to let these crystals form. But now, how do we not let these crystals form? We need to design the compositions in such a way that these crystals do not form, right? Even if the temperature goes down, the crystals should not form. These spinel crystals should not form. So the scientists or the engineers working over there at Hanford site, they came up with these two empirical constraints, and there is no scientific basis to these constraints. It's just like, know-how. Oh, I feel this should be the case, so they put this over there, right? So what they said is, oh, you know what we need to do? We need to put a restriction there that we will design the composition in such a way that even if the temperature of the melter goes down by up to 950 degrees C or 850 degrees C or 900 degrees C, the amount of crystals that form in the melt should not exceed 1 volume percent. If the amount of crystals that exceed 1 volume percent in the glass composition, we will not use that glass composition in the melter. So they put a restriction over there. That's constraint. Now, in the research scale melters, we have seen that we can go up to even 4 volume percent of crystals, and melter still works fine. So this 1 volume percent actually out of just somebody's assumption, it's highly empirical. There is no basis to it. And in this figure, you can see if we stick to 1 volume percent, we'll have to produce 25,000 metric tons of glass. But even if we can reduce it to 2 volume percent, even if we can increase this tolerance level to 2 volume percent, now we are talking about 23,000 metric tons of glass. So basically, we have immediately reduced the volume of glass by 2,000 metric tons. That's huge. And if we can go to 3,000 or 3 volume percent, now we are talking about 22,500 metric tons of glass. So if we can increase the amount of crystals that the melter can tolerate, the amount of glass that will need to be produced will reduce, right? Another constraint they put in there was the liquid of temperature of the melt of the composition have to be less than 1050 degrees C. Now, this constraint has no impact on any processing or anything. It was just a safety margin they wanted to keep, which has been proven that, it has not led to anything fruitful. In fact, on another site at Savannah River in South Carolina, they have actually seen that due to this particular constraint, they have been able to produce 15% lower waste loading in the glass. In other words, if this constraint won't have existed, they would have produced 15%. They would have added 15% more waste to the glass, right? And still got a good glass out of it. So now these two constraints, I hope you can imagine now that these two constraints are limiting our ability to produce glasses. So now the goal over here is how we can replace these two constraints, empirical constraints, with something more scientific, something more rigorous. So that's where scientists like us, we come in, where we work on these compositions. We try to understand them from the very fundamental science perspective. What is it in the composition and in the atomic structure of these glasses that is leading to the formation of these, spinels in the melter? And if we can understand the drivers that are driving the formation of spinels, we can suppress those drivers, we can tune those drivers so that the spinel formation is suppressed, right? And around that, then we try to develop models that can predict spinel formation in the melters, because we understand the fundamental science, but those guys who are melting the glasses, they are engineers or they are technicians. They do not understand and they do not care about the science. All they need is a software or a model where they can chug in the numbers and they can see, will this composition form spinels or it won't form spinels, right? So we are working towards that. That's one problem. So now that was inside the melter, right? Now imagine you have melted the glass and spinel, like there was no idling situation. We formed the melt. And now the melter is ready to come out of the, now the glass melt is ready to come out of the melter, and we are going to put into a steel canister. So now when we put this melt into a steel canister, what will happen is, there you go. So there's a steel canister, and there comes the melt, and you can see the steel canister is filling up, right? Now, as the steel canister fills up, the very first layer of the glass melt at the bottom, it will be in touch with the steel, right? The very first spout of the melt that comes out, it will be in touch with the steel canister. So now steel is a good conductor of heat. It's metal, right? It's good conductor of heat. It will immediately quench the melt and will turn, see, it will turn the melt to glass. But the next spout of the melt that comes in, it will not fall on the steel, it will fall on the previously laid glass, right? And glass is a bad conductor of heat, or it's an insulator. So eventually, what I'm trying to say over here is that the heat will start to build up, and what will happen is the maximum heat will be built up at the center of the canister. Due to that heat build up at the center of the canister, there will be nucleation and crystallization in the melt, in the glass, right? And due to that nucleation and crystallization in the glass, a particular phase called nepheline gets formed. Now, nepheline is a sodium aluminosilicate phase. And if you have studied a bit of, glass or ceramic processing, and if you know what are network formers, network modifiers, you will understand this, that sodium oxide is a network modifier, and alumina and silica are network formers. And you need network formers to make glass. More network former means better glass or durable glass, right? But if you look at it, for every 1 mole of nepheline, that is crystallizing out of the glassy matrix, you are taking out 3 moles of network formers. So basically, when the crystals are being formed in the glass, for every 1 mole of crystal being formed, 3 moles of network former is coming out of the glassy matrix and going into the crystal. So the remaining glassy matrix is becoming less and less durable. You do not want that. You do not want your nuclear waste glass, final waste form to have poor durability, chemical durability, right? So that when it comes in contact with water, you do not want it to dissolve, or do not want it to, like the radionuclides to release. So we have to meet the current disposal requirements, and for that we need nepheline crystals to be avoided. We do not form nepheline crystallization to happen in the glass, in the waste form. Now, to predict that whether a glass will crystallize nepheline or will not crystallize nepheline when poured into a steel canister, different models have been proposed by national labs. So these are the 4 different models that have been proposed by national labs. Recently, now with the advancement in machine learning, now we are also combining machine learning models. So there are 1 or 2 more machine learning models that have been proposed. They haven't gained so much of traction. These are the 4 primary big models that have been discussed in the literature and have been, used in the studies. So these models have been proposed. Now the problem with these models is, they work for a good chunk of compositions, but all these models are empirical in nature, right? So they have been based on data, like machine learning. Machine learning is all about data, nothing else, right? So similarly, these models are empirical models which have been based on data. So now what happens is, when they are not based on science, they are based on data. They do not tell you what is going on. Why is this model making this prediction? What it tells you is just whether it's a go or a no-go, whether it will form nepheline or it will not form nepheline, right? So in that case, what happens is, there are a lot of things, like where a model, for a lot of compositions, these models fail. Like it will tell you that, okay, for this composition, I do not expect nepheline, but then actually nepheline shows up. Or on the other side, it will say, oh, no, the model, these models will predict for this composition, we expect nepheline to show up, but actually nepheline doesn't show up, right? So what happens? So what is it that we are looking for? We are trying to figure out what's the fundamental science, again, that is governing this nepheline crystallization, nepheline formation in these glasses. What is it that triggers or that suppresses nepheline crystallization at the atomic level, at the fundamental level, so that we can make quantitative structure property relationships from these, to predict nepheline crystallization, which are based on fundamental science, not on empirical studies. So for that, we have been working in our lab on this topic for the last 10 years. And our strategy has been, where we started with a very simple 3-component system. From 3-component system, we made it a 4-component system, then to a 5-component system, then to a 6-component system. And that's how we are increasing the complexity. And we have reached to a point. And you can see, like all these papers over here are from my lab. And, we have reached to a point where we have now proposed in this paper over here in Goel et al. Acta Materialia, where we have proposed a quantitative model based on molecular dynamics simulations to predict nepheline crystallization. And we further intend to refine it with more and more experimental data as we produce in the future studies. All right. So that's where we are for the future, Then comes in the, the third part. Now imagine like, okay, we made the glass, we melted the glass, we packed into the steel canisters, and now that steel canister will be shipped to geological repository. Now, when it goes to the geological repository, that steel canister will actually be packed in, layer after layer as barriers. So for example, you can see on the screen over here, this is the steel canister. It will be packed with carbon steel, then it will be in sand and betonite, and then it will go into a geological repository, engineered geological repository. So by the time when it, let's say, and tomorrow, thousands of years down the line, let's say, water breaches into this geological repository, because, eventually it's going to corrode, right? Like the geological repository will come in contact with water, will come in contact with bacteria, will come in contact with all the microorganisms, they will eat over it. And eventually, when in future, sometime, if all these barriers are breached and the glass comes in contact with underground water, how will it react? So now it will not be only water. Think about it. It will also be all the sand, all the concrete, all the steel which was around it, everything. So the pH of the water will not be the pH of pure water. We are talking about alkaline pH or neutral to alkaline pH, right? Or it can even go to hyperalkaline pH depending upon what kind of repository we build over there. So in that case, how does the glass corrode in that environment? What is it that drives the corrosion of glass? We usually think that glass is actually an inert material. No, that's not the case. Glass is not inert. Glass, it's the kinetics. Some glasses dissolve really fast. Some glasses dissolve or react really slow. But they do that whenever they come in contact with a solution. Even when a glass comes in contact with water, it starts to interact with water, or acid or base. Glass corrodes. So how does a glass corrode over time? There are a lot of questions around it. I won't go into a lot of detail here, but there are a lot of questions around it. The corrosion of glass can be divided into 3 different stages. This is stage 1, where ion exchange takes place. Sodium, calcium from the glass, they go out and are replaced by sodium ions, basically Na plus, Ca2 plus, for example, they go out from the glass, and ion exchange of hydronium ion goes in for charge neutrality, right? Na plus goes out, H plus goes in, or H3O plus goes in, hydronium ion goes in, ion exchange. Over here, you get a silanol layer. You guys are chemistry students, so I'm assuming you should know what is silanol. SiOH layer forms over here. And then over here, you get a saturated solution where you start getting precipitation on the surface of glass, and different phases form on the surface of glass. So, that's how the glass starts to corrode. It's the kinetics, like how fast or how slow the glass will corrode, what will be the products that will form, and when those products form, how are they going to impact the further corrosion of glass? Will they protect the glass from further corrosion, or will they enhance the glass corrosion? All these mechanisms, they come into play. And that's what scientists work on quite a lot in this topic.
So give us about 2 more minutes, so we could get questions.
Right. So there's a lot of research to be done on glass corrosion. In fact, a lot of my research is on glass corrosion. Several of my PhD students and master students have worked on glass corrosion, on nepheline crystallization. In fact, one of my PhD students also worked on nepheline spinel crystallization. So in summary, what I'm saying over here is that, okay, the Hanford site in Washington state is home to 56 million gallons of radioactive waste. The waste will be categorized into high level waste and low activity waste. The low activity waste has vitrification of low activity waste has started in 2023. Vitrification means making glass, turning something into glass is called vitrification. The vitrification of both the high level waste and low activity waste is really complex. The process is really complex. There are several challenges we need to address. What I have discussed over here is only 3 crucial problems. Low activity waste has its own problems. I discussed the problem only related to high level waste and only 3, right? And we are always looking for good undergrad and PhD students, master students to work in this area. We usually have funding. If any one of you is interested, if I am able to motivate any of the senior year students or a junior year students, you're more than welcome to apply for a PhD program at Rutgers, and we'll be happy to consider your application. With that, I'll take any of your questions. Thank you.
Okay, thank you. So you guys could use the chat to put your questions in. Not sure if this is going to work, but we'll try at least the chat. Any questions to get started? Ian? Huh? Okay. Okay,
So
I don't know if
there
you've
is a
heard.
question. There is a question over here from Annalise.
Right, but we had a verbal and oral question, and it was, how difficult, relatively speaking, is it to form glass from nuclear waste versus a normal borosilicate glass? Roughly? Yeah. Okay,
How difficult is it?
yes, compared to forming a normal glass.
Okay, so a normal glass, like I'm assuming you're talking about, let's say, your container glass or your window glass, right? So that's a pretty simple chemistry where you take sand and limestone and baking soda or washing soda, and you mix them in a proportion, and you heat them to around 1,600 degrees C, and you get a glass out of it. There's no much challenge to that. In this case, you're talking about almost half the periodic table going into it. So, making glass is not a problem. The problems come from all the process related challenges where, like you have, like I showed, like, for example, spinel crystallization in the melter, right? The melter stops working. What do you do in that case? Or once the glass has been made, nepheline shows up, nepheline crystallizes in there, and now you have got a problem with chemical durability. Or during the melting of the glass itself, this radioactive waste, it has a lot of fission products, which are actually noble metals. So a lot of times nuclear fission reactions take place, eventually resulting into noble metals. And those noble metals have very high density, and they settle down on in the tanks. And when they swirl the tanks and then they push this waste into the melters, the noble metals, they are noble metals, right? They do not want to react. So they do not want to be a part of the glass. They just settle down in the melter also. So that's a huge challenge. Now, what do you do? So, engineers work on it whenever they have such problems. Japan has worked on it quite a lot. They learned from the mistakes what the US did. Japanese had actually huge failures, and they learned from their own failures, and then they revamped the design of the melters with that. You do not face all these challenges when you are making a window glass or a container glass, for example. It's run-of-the-mill job. Once it is set up, it's set up.
Okay.
I hope that answers your question.
So let's see, Annalise has a question there. You could see that in the chat?
Yes. So Annalise says, if it was possible to saturate glass with nuclear waste, the glass would not be able to be of use for conventional purposes. But could we repurpose the nuclear glass for other things? Have you seen any areas where this waste saturate glass could be used for productive purposes other than being stored away to decompose? Yes and no, both. So the nuclear waste glass in itself does not have any application because it's radioactive in nature, right? I am also a former national lab. I was a scientist at Pacific Northwest National Lab before I became a professor. And at that time, there was an idea discussed at that time that, hey, these steel canisters, they are pretty hot, right? So why can't we use their heat to, light up something like, for example, to heat up a fuel cell, a solid oxide fuel cell, because solid oxide fuel cells, they require very high temperatures. Can we use the heat being emitted from these steel canisters to, fire up solid oxide fuel cells? Theoretically, it's a good idea. But then who's going to deal with all that nuclear waste, all those nuclear waste canisters? Because eventually those canisters are also going to be radioactive because they are being exposed with all those radiations, right? Coming from inside of the waste glass. So that's one. So nuclear waste glass, I do not see any sort of an application because you do not want humans to interact with it much. But before that, for example, from the nuclear waste itself, I have seen, like in India, for example, they have extracted cesium-137. So cesium-137 is one of the most highly radioactive compound or radionuclide present even in Hanford waste in the US. In India, they actually extracted cesium-137 out of their waste before they vitrified it, before they converted it into glass. They extracted cesium-137 and then they used that radioisotope for the medical purposes. Okay, as nuclear medicine, in nuclear medicine. So depends, what is it that you're looking for? Some countries have used that, not glass, but from the waste, extracted and then used it. In the US, we don't do that.
Okay. So to be sure, the glass is still radioactive, correct?
Yes, glass is still radioactive.
Okay. Okay. Just making sure. Other questions?
I was gonna ask, like, what the activity level is, like, depending on what's selected, or, like, is the glass really highly active? Or is it more, like, by the time they go, with the activity, and die down?
So you may have missed, I think, the first part, right? Because he said that basically the waste is divided into low active and highly active.
Low activity waste and high level waste.
Yeah. So they
Okay.
do that
If the
separation.
level of waste is turning the glass through, it's like the active components still make it behind, but like,
Yeah, it's still very high, right? The activity, the
What's the
radioactivity.
question here? What's the
The
question?
radioactivity of the high level glass, it doesn't decrease, right? It's pretty active still.
So the radioactivity of the high level waste glass primarily comes from cesium-137 and strontium-90.
Okay.
They are two highly radioactive species present in high level waste. Before the high level waste goes to the vitrification plant, right, to be converted into glass, all the attempts will be made to extract cesium-137 and strontium-90 out of them. But it is still anticipated that, few percent of these two isotopes will still remain in high level waste, which will make it radioactive.
So cesium and
All
which
right.
was the other one?
Strontium-90.
Strontium. Okay.
Cesium-137, strontium-90.
Okay.
So yeah, they have made arrangements to extract these, to remove these isotopes from the high level waste. But hey, you cannot guarantee that you'll extract all the 100% out of it. And even if you do, due to the radiation from these two isotopes, when it is in the nuclear waste, right, all that heat, all that radiation being emitted will lead to further reactions within the waste and can lead to other fission products, which you don't realize, which we don't know.
Right.
So, yes, you'll consider high level waste glass to be radioactive.
Any other questions?
I have a question. Suppose in the future we desire to use this high-level radioactive waste somebody developed a way to develop, power out of the strontium, the cesium. How difficult do you think it would be to reconcentrate these things out of the glass? Or is this a permanent fixation of those isotopes in that matrix?
Can you please repeat the question, Desmond?
So I think what he's asking is,
Right.
if in the future we want to
Mhm.
use some of the elements like the cesium or the strontium in the glass, how
Mhm.
easy would it be to like extract it out,
Right,
reconstitute it?
reconstituted,
yeah.
increase its concentration. that kind of
Yeah.
thing. Or is this a permanent embedding
Yeah,
of these things in the matrix
yeah.
of the glass?
Is this
It
for all
is
time?
so that has been thought of, and it is, in our case over here, it is a permanent embedding. If you want to extract cesium or strontium out of the glass tomorrow, and let's say 100 years down the line, right? So you will have to take the glass out of the repository and break all the, like, you'll have to take that package out. You'll have to break all the barriers, or like all the shielding around it, and all the whatever betonite and carbon around it, rip off the steel canister out of it, and then reach to the glass, and then take the glass out of it and dissolve it into some acid to extract strontium and cesium. I don't know if it's that worth of it.
Right.
Yeah. So one of the things that students should be aware of, I think some of my organic chemistry students are starting to be aware of it, is that glass could absorb and does absorb water because of those silicon oxygen, silicon OH bonds undergoing hydrogen bonding. So it doesn't have to do with nuclear waste, but being able to understand that the surface of glass could be wet even though you don't see the water. Okay, any other comments, questions? All right, thank you so much, very much, because this is a topic I don't think we do a lot of in, go ahead. What's the best way to store?
You didn't say too much about where they're storing the glass.
Yeah, do we know yet where they're storing the glass?
Right, like where are they storing the glass for temporary case right now, or permanently where is it going to go?
He's asking permanently.
Yeah, where is the glass being stored permanently?
Only the future presidents know that.
Okay. To be determined, huh?
Yeah.
Okay. All right,
Again, thank you
well,
very much.
thank you so much.
All right, sir. It was a pleasure. Thank you. Thank you for inviting me over.
Okay, thank you. Take care.
Take care. Bye-bye.
All right, bye-bye.
Because in 100 years, you wouldn't need these guys to come up with a use for it. We don't have it.